Okay, so good morning, everybody. So my name is Maxime Martinasso, so I'm part of CSCS. So today we have the course on Intel KNL. So first of all, I would like very much to thank all the Intel people here that came and made the course available for us. It's very nice, very appreciated at CSCS. Thank you very much. I also find that it's quite an interesting technology with a lot of capabilities, so I'm very eager to know more about it. So here at CSCS, we have a TDS machine, so a test and development system that contains KNL. So it's a Cray system with 164 nodes. Each node has one KNL, and we will use that machine during the course. So it will be available for us up to 6 p.m. on Friday. So if you need to run things, or if you want to run large jobs and things like that, so we can also run them overnight. So please come to me and we can arrange this. You can also, if you want more, you can also ask for a development project with CSCS if you have access, if you are eligible to run on CSCS machine. That will give you 36,000 node hours that you could use for your development to help you, to develop your application and see the performance on the KNL machine. Regarding the organization of the course, so here's the agenda. You can also find it on the web page where you registered for the course. So we have breaks and lunch, you see. So lunches are for 1 hour and breaks 30 minutes, so please be on time. They will be here in the hall where you got the coffee already. Wi-Fi, it's here, but you also have a folio on your desk. So there is also ETH and EduROM access if you need for the Wi-Fi. And the video, so everything will be recorded, hopefully properly. And so if you have, so the video will be initially for our internal usage, but we maybe try to get them on the public. That will depend of our interaction with, with procurement and things like that with Intel. And if you have a question, you shouldn't use a microphone. Okay, then otherwise there will not your question will be not recorded on the audio. So with this, I think I'm done. So I'm very pleased. So, Michael, please.
All right. Good morning. Welcome. Are you feeling happy? Are you feeling good? Okay, let me change that. All right, so this is the agenda. There's a usual disclaimer I want to make for each of the agendas. It's a rough guideline on what we want to do. If you think that you want to hear on a special topic, let us know and we're going to change the agenda, right? This is your workshop, it's not our workshop. If you want to hear something, let us know and we will tell you about it, all right? And the other thing I would like to make is make this as interactive as possible, okay? The more you ask questions, the less slides I'm going to show, okay? So this is usually a good thing. So raise your hands. I think Maxime will run around with the microphone and then, we should make this as interactive as possible. Okay, agenda-wise. So I have the pleasure to start this. I'm going to tell you about the Knights Landing architecture, a couple of programming considerations and the microarchitecture of it. Then Hans Papst, so we have this nice acronym codes that we invented for this workshop. Then Hans will take over with how you program this thing called MCDRAM, so the high bandwidth memory that is on this nice chip. Then there are KNL system tips. Whatever's supposed to hide under that agenda item, I don't know. I'm curious to learn that as well. Then we're going to have lunch, and then we're going to talk about the details like compilers, the advisor, all the tools that are somehow associated with Intel architecture and the Intel processors. And you can of course play with that. The next day we're going to focus on MPI, OpenMP, tell you a couple of specifics that are relevant when you want to program for a Knights Landing, and show you how the latest developments of OpenMP and how you can use that for KNL. And then, there's also an app session where we are going to tell you just a little bit about what we did for applications. It's more like a case study. so that you can see, what optimizations we did, what effect they had on the code, and, so the takeaway should be, some recipes that you might find useful for your own code. And then the other thing, day 3, same thing basically. We're going to start with an app session. I'm going to tell you just a little bit about OpenMP 5. So this part is not an Intel presentation at all. And what you will see, and will likely change over the next couple of months, but still, it will give you an outlook on what will be coming in 2018 with OpenMP. And then Hans will tell you a little bit about machine learning, small matrix multiplies, and that kind of stuff that is also relevant for some applications. KNL, Knight's Landing, code name, the now Intel Xeon Phi processor. That's the brand name for it, but I'm going to talk about Knight's Landing and KNL all over the place. Usually the community knows the code names better than they know the marketing nerds. The other thing is, that's probably the most important slide in this presentation, the legal disclaimer, and you can't blame Intel for that, and some other stuff, like trademarks and so forth. Okay, so what I'm going to tell you is, first of all, give you the idea of KNL as a processor architecture. What are the features that you can expect, and that kind of stuff. And then we're going to talk about the core architecture. So that means the individual core, and how they are connected on the processor die. And then we will talk about the untile architecture. So if you know Xeon processors, we talk about core and uncore. And for Knight's Landing, we talk about tile and untile. So everything that is not within a tile is called the I think a colleague of mine invented the term. All right, so high-level overview. No Intel presentation without lots of space. It has 8 billion transistors, so it's probably one of the biggest chips on the market. I think only NVIDIA has more transistors to offer. It's manufactured in a 40 nanometer process, so that's kind of bleeding edge technology at Intel and across the industry. It's a pretty fascinating processor architecture. Okay, so, well, it still says coming 2016. I should probably update that slide. But basically, if you have seen Knight's Corner, the Xeon Phi coprocessor, the Knight's Landing processor is kind of a natural evolution of that concept. We forget about the coprocessor thing. We just make it its own bootable processor. It delivers more than 3 teraflops of peak, and I will have a slide in a minute that shows you that we actually do that. There are 16 gigabytes of high bandwidth memory, lots of DRAM, so all the weak points, I would say, of the Knight's Corner coprocessor should have been fixed for the Knight's Landing processor. And it's also not a one-hit wonder. There's also Knight's Hill on the roadmap. And for those of you who have a restricted secret NDA with us and have seen those presentations, you basically already know what will be coming in Knight's Hill. Right? So there's a next generation planned already. Okie dokie. There are 2 major versions. And I'm kind of focusing on the KNL processor for the rest of the presentation. There is still a coprocessor for those crazy folks who really need a coprocessor. But the main effort at Intel goes into this Knight's Landing processor architecture. There are 2 versions of that. There's the host processor, and then there's a host processor with integrated fabric. So that's the little balcony attached to the processor package. That's where you hook up the OmniPath fabric, and then you have dual link into the rest of the system, basically. Right? Okay, so what we try to do is when you compare the coprocessor and the Knight's Landing processor, or if you compare a Broadwell processor with the KNL processor, you will see that we have about 3 times the single thread performance compared to Knight's Corner. Who of you did program Knight's Corner? All right, have you been happy with the single thread performance? No, not at all, right? There's always some sequential fraction in your code, and this is going to help, It's not solving the problem, to be honest, but at least it's helpful, right? It's not a real kicker in terms of performance drops that hits you. Compared to a Broadwell, we'll close to 1/3 of single-thread performance. So, still, if you have something that is really single-threaded, Xeon will still be the better choice, right? I'm not trying to sell KNL as the holy cow of processing, right? There are still performance gaps that you will see if you have large single-thread portions in your code. What else? Well, the highly parallel vectorized code executes about 2 times faster in each cases. There's memory bandwidth is a lot higher on Knight's Landing. It was also a rather weak point on Knight's Corner. At that time, compared to Haswell or Sandy Bridge, Ivy Bridge, it was still good, but compared to Broadwell, we had to do something. And then the single node power, since we don't need the host system anymore, it's a lot less power and more power efficient than before. Okay, and it's also more energy efficient than the Broadwells. All right, what else? What it is meant for? That's probably the big decision that you have to make. Is the Knight's Landing processor the right compute capability for my application? Right? And there are some applications where we say, yes, that's a nice fit. And then there are other applications where you rather should stick to something like Xeon. Okay? And those basically that are very applicable are marked in green. So that's where we also have proof points that we already published saying, this is what you can get out of the system for this kind of applications. Then in bluish color where we think it's applicable, but it's a lot more work, right? And then everything that is white is basically where Xeon is the better choice. So for instance, just to make a bad joke, email, you shouldn't run your Exchange server on a KNL processor, right? Apart from the fact that Windows doesn't run on it, but you shouldn't run Major Domo or anything that handles emails on it, or web servers or print servers, right? There's some workloads that don't fit. All right. Again, there are different models with different price tags. So if you want to know what the price tag, the list price is, go to arc.intel.com. Of course, then there's the real price that is charged when you buy a real system from Cray or from any other vendor. But basically what you can get is different flavors of the product that basically varies in the number of cores that you get and the frequency that those cores run at, and that also have a different power envelope, so take different power from the system. Right? And which version do you have? I think you have this. 2230. This one, 64 core? Yep. Very good. So this 27230, that's the one you have in the test system. Okie dokie. It also has turbo mode. So it's basically the same thing as with the Xeon processors. So we have a frequency that's the model-specific frequency, the ISO frequency. And then, there's turbo mode, so we can slightly crank up the frequency if cooling is sufficient, if you have sufficient power supply, and the boundary conditions are okay. And then again, there's the AVX frequency. So that means when you use high power instructions like AVX 512 instructions, then the cores clock down just a little bit. I think it's 200 megahertz or something. All right? But then again, the turbo mode can kick in and can crank up the frequency just a little bit, to compensate for that loss. All right? Again, turbo mode is opportunistic. That means there are no guarantees that you will run at turbo mode. Okay, it's just a bonus that you will get from the architecture, and we cannot guarantee for all the boundary conditions that need to be satisfied so that the frequency actually goes up. All right, now performance. So this is now, double precision gigaflops at TDP frequency, so the frequency we sell the processor at, and as you can see, that's Broadwell, That's the old Xeon Phi coprocessor, 300 watts, and this is now Knight's Landing, and you should expect something like 2.6 teraflops peak performance from the system you have in your TDS system. Okay, so that's a considerable speed up for anything that is floating point heavy. Okay, DGEMM performance. If you care about DGEMMs, this is again your processor, so you could expect something like 1.8 teraflops double precision DGEMM performance for a single node. Okay, that's about like 60% more than what a dual socket Broadwell node currently does. Okay, that's now stream benchmark. So you can see that a Broadwell node is about 120 gigabytes per second memory bandwidth in stream triad. And with MCD-RAM, I should probably take that number again because that's your machine, you see something like 740. So that's a rough 3.7-fold increase in memory performance. Okay, and that's something where if you're really memory bandwidth bound, you can really get a performance benefit out of using the high bandwidth memory on the processor package. I will say something about latency versus bandwidth in a couple of slides at the end of my presentation, so there's still some caveat to be aware of. Okay, who likes it so far? Good. Who thinks that such a beast is really easy to program? It's like, yeah, I take my makefile and I add a new compiler flag and I'm done. All right, who says, nah, that doesn't work? Okay, there are a couple of people that didn't raise their arms. Are you just asleep or you don't care? All right, okay. Okay, tile architecture. So this is how KNL looks like when you take the chip and you dive into it. So let's dissect that. So we have those little yellow boxes in here. That's what we call a tile, and I'm going to explain in a minute what a tile actually means. So we have like 36 of those tiles that are connected by a 2D mesh. So if you recall something like KNC, Knight's Corner, we had rings, ring buses. If you think about Broadwell, we have 2 or 3 rings that we connect to each other. And here, this is the first processor that has a 2D mesh. Well, from Intel, okay? Not in general. And actually, it's not the first one. We had the single chip cloud that also had a 2D mesh, but details. Okay, so all those tiles are connected by a 2D network. To the network attached, there are those gray boxes. That's the MCD-RAM memory controllers that drive the high bandwidth memory. For those who are interested in acronyms, MCD-RAM is multi-channel DRAM. That is on the package. Then there are blue boxes. That's the memory controllers for the DDR4 memory. So 6 channels of those. And then there's a red box that contains kind of the rest of the infrastructure and the connection to the outside world, so PCI Express, DMI, whatever we need so that this appears to be a full processor. Okay? Now for the tiles. One of these guys here is actually a dual core tile. So in there we have a shared 1 megabyte L2 cache. All right, so this cache is private to a tile, but it's shared between the cores on that tile. Then we have 2 cores, 4 VPUs, and a hub. And there's one issue that I have with this slide and the way we depict the tiles here. These VPUs are not extra units on the tile. They are actually in the core, but for marketing reasons, we call them out as, this is now the shiny thing in this tile, but actually you should more think about this being one core and this core being another core, okay? And the hub basically now is the little silicon piece that connects to the 2D mesh, right? Make sense? Makes sense, good. Okay, instruction set wise. Who still remembers, I'm trying to keep you awake here. Who still remembers that Intel was telling you that there will be converged instruction sets starting with Knight's Landing? All right. they converged, but at the same time, they also diverged again. And what I mean by that is the following. So going from Xeon Broadwell to Xeon Phi processors, we first of all kicked out transactional software extension or transactional synchronization extensions. Right? That's a feature that Intel considers to be an enterprise feature and not so much an HPC feature. We have some HPC customers who are looking into that, but it's more like databases and where you have unpredictable locking. So that is gone. Okay, we don't support that. But what we do support is AVX 512F, and the F now means foundations. So that's a common instruction set, and that's why I said it converged. That's a common instruction set that will be common and shared between Xeon Phi and future Xeon processors. And I think when I look in your faces, you can also pretty much predict what this future Xeon processor will be, right? It's almost here, right? It's going to launch soon. Okay, so this is common across Xeon Phi and Xeon. There's also another package which we call CD for conflict detection. That's a couple of vector instructions that help you detect conflicts when you write back to memory with a scatter operation. You can detect potential race conditions between writing elements of a vector, and then you can go back from vectorization, do something scalar, and then switch back to vectorization. It's an easy check to see if you can vectorize something. That's also common. But the instruction set kind of diverges when it comes to the additional stack that are HPC instructions. So we have prefetching instructions on Xeon Phi. So you can issue software prefetches. And we have ER. That's special instructions for exponentials, reciprocals, square roots, and that kind of stuff. And we have machine vector instructions for that. Okay, so you can do a vectorized square root, reciprocal exponential logarithms, and that kind of stuff. They're not, as far as I know, not IEEE, but they have like 2 to the power of minus 28 accuracy. So they're pretty accurate. Yes, there's a question.
So do you have any instructions for complex?
No. Okay, and the Xeon processor will have DQ and BW. That's now double quad word and byte-wise instructions that we need, for more general processing like genomics, integer math, and that kind of stuff. All right, so that's where Xeon slightly deviates from what Xeon Phi does. Okay, caches. It's basically the standard thing. So the L1 cache, which is, inside a core, that's an 8-way associative instruction cache, 32 kilobytes, or data cache, the same thing. Then there's the L2 cache, 1 megabyte. So it's a 16-way unified cache. So both cores will see the same cache, and they will dynamically distribute the cache line between the cores. So effectively, if you have, real disjoint data, you have like a 0.5 megabyte per core cache in a single dial. There's also TLB. It's 48 entries, 64 entries, and then there's a level 2 cache that has a much bigger entry set. And it also supports 4 kilobyte pages and 2 megabyte pages. So there's also support for huge pages as well. Okay, then it's called hub here, but actually it's caching home agent. So that's the guy that takes care of talking to the rest of the system. It contains the distributed tech directory. So on the chip, we need to store information about which core has which cache line. That's called the tech directory. So this is distributed, and it implements a massive protocol. So modified, exclusive, shared, invalid, and then F for forwarding. Since we don't have an L3 cache, well, not necessarily an L3 cache, what we can do is, if we know that the cache line is already somewhere on the chip, we have the forwarding state to send a request to the owner on the chip. So we don't necessarily need to write back to memory and then get it back from memory to get it into another L2 cache. We can forward the cache line through the chip, and that's why we have this F state that indicates that the cache line has been forwarded to somebody else. All right? Okie dokie. This is now, if you're really interested in it, probably I will, yeah, come on, I will skip it because you're not really interested in Atom processors. This is just to show that we really extended the core technology of the individual cores based on Atom. But since Atom is a client core, we had to make some considerable extensions. This slide basically lists all of them. Okay, the core. I already said that the VPUs are an integral part of the core architecture. It's not that they are separate units somewhere. And if you recall a pipeline picture of Broadwell, you will see that this is a lot easier pipeline. All right, so the Xeon pipeline, and this is where the processing power and the single thread performance of Xeon comes from. The pipeline on a Xeon is a much more complicated beast than this one. All right? Okay, let's go through it. So there is a front-end unit. It basically does the same thing as on Xeon. It takes the instructions from the instruction cache or from memory. It decodes them. And what we can do is we can actually feed 2 instructions per cycle from the decoder into the reservation station or the rename station that basically takes care of assigning an instruction to the individual execution pipelines. Okay, there's a 32-entry instruction queue, and we have, it's called cheese queue style. So basically what it does is there is a branch predictor. It's less powerful in what it can predict than Xeon, but what it does is it combines a couple of different brief prediction approaches, and that's why it's called cheese queue, because there's different approaches to do that. What exactly we do, I can't tell you, I don't know, and I'm probably not supposed to tell you anyway. Okay? Okay, so there's a branch predictor, and then the next thing is that we feed things into the allocation unit. So this is now, on Xeon we call that reservation station, here it's called allocate. So basically that's the unit that takes the micro operations that come out of the fetch and decode pipeline stage and assigns it to the individual execution unit. So then we know it's a vector instruction, it's a load, store instruction, or whatever we need to do, or it's a sequence of microcode operations that we need to execute. We have 72 entries to do reordering. Just to give you a number, Haswell had 192. Okay, so sometimes you read something like a shallow out of order engine. Right, so it's just less capable than Xeon, because we need, reorder buffers need power. It's a lot of effort in terms of silicon that goes in there. So we had to, make that a lot simpler than on Xeon. We have a rename buffer that basically takes care of register renaming, and then we have, additional buffers and tables to take care of stores and gather scatter operations so that we can speed them up and execute them. Okay, there's an integer unit. We have 2 of them. So you can basically assign 2 micro operations per cycle and also execute them. They are also out of order. Most instructions take something like 1 cycle in throughput. There are some instructions, like for instance multiplies, that are rather lengthy in terms of cycles, and they can only be executed on a single port in that picture. Okay, so if you're heavy on those instructions, you will see penalties in terms of performance. Okay, recommendations. The Knights Landing processor is a floating point device. So what our architects did is they really tuned the system for floating point performance. If you have an integer workload, be aware that integer instructions are not giving you probably not the expected ideal optimal performance. Right? It's a floating point device. Okay? We can still execute them, and you should basically, if you know what your integers do, like it's a shift right, shift left, and or whatever operation, then try to use those as much as you can. Use the simple instructions instead because they're much easier to implement, and try to avoid scalar code whenever possible. Right? You cannot do it, loop counters and such, and memory address calculations. but basically don't try to run an integer-only workload. That's what I'm trying to say here. Okay. Okay, then there is the memory execution unit. That's the green part in here. That's now where we load and store everything from main memory and the caches. We can execute 2 micro operations, or we can dispatch them. So either a load or a store. But they are dispatched in order. So this is now not an out-of-order engine. So we dispatch them in the order as they are arriving to the system or from the dispatcher. But they can at least complete in any order. Okay, so we're not bound to wait until the first one that we dispatch actually completes until the second one can complete. We have to dispatch them in order, but they can complete in any order depending on the memory latency. All right? We have 2 ports for 64-byte loads. We have one 64-byte store port for the data cache. Now the thing is, that's now for L1. For L2, we support 1 line per cycle to read and half a line per write. Okay, so it's full bandwidth for reads, half bandwidth for writes. There's an L1 and L2 prefetcher, so that means the prefetcher in the system take care of moving data into L2, from L2 to L1, and then into the cores. We have fast support for unaligned and cache split support, so that, but still, you need to take it with a grain of salt. If you think about something like SSE, you know what a split load is? A split load means that a vector register comes from 2 cache lines. So one part is in one cache line, the other part is in the other cache line. Right? If you think about SSE, you have a split load every 4th load. Right? AVX2, double the vector width, it's every second. For AVX512, it's every load that is a split load. And even though it says fast, it doesn't say free. Right? It still comes with a cost. It's just not as painful as it was on Knight's Corner. Okay, Knight's Corner, you had like 5 times penalty if you had a split load. Here, it's a little faster, but still you have to pay for it. So if you can align your data to be cache line aligned, you have to do that. And then we have fast gather-scatter support. So now the execution unit actually understands the micro operation of gather and scatter. On Xeon, it's a microcode sequence. So the decoder creates a loop, basically, that executes a couple of micro operations. On KNC, it was horrible. Right? On KNC, you had to have a loop that basically does the gather operation. Every time there was a cache miss, the gather operation would stop, and then you would have to set it up again, and there's a mask register that basically tells you how many of those elements that you want to gather have actually been loaded. And you basically run the loop until this mask registers is all 0. Okay, so that's why we say it's fast gather and scatter support. Again, you have to pay a price for it. It's okay, right? But if your data is aligned such that every element comes from a different cache line, there's a price you have to pay, and there's nothing the hardware can do about it. All right? Okie dokie. Recommendations. I said that. And then there's, of course, a little penalty if your split load goes from one page to another. And in those cases, it might be beneficial to introduce software prefetches into L2 to prefetch a couple of L2 lines from the next page already while you're still executing on the previous page. Okay, but that's now hard to get right because software prefetches may interfere with the hardware prefetcher, and so it's really a tuning exercise. Okay, floating point unit, basically 2 of them, left and right. We have 20 entries that we can execute out of order. We can complete 2 512-bit FMAs per cycle. Most of the operations take something like 6 cycles. So this is now, throughput case. And we also have, of course, x87, MMX, and SSE instruction support. Again, probably it's not a wise idea to do that, right? So x87 shouldn't be used anymore. We still support it, but performance will be so-so. Okay? Okay, VPU recommendations. I already kind of indicated that. Don't use x87, MMX, SSE, or AVX2 at all means. It's an AVX512 floating point device. That's what it's meant for. We support it for compatibility, but not for performance. Okay? Not necessarily for performance. Okay, the other thing is, if you wrote intrinsic code for Knight's Corner, who did that? You can admit that. Come on, we're a small community. I'm not gonna tell anybody, and we're gonna bleep it out on the video. No? Okay. So, okay, then I can, but basically if you have intrinsic code, you probably need to rewrite it to choose the ideal instruction sequence for the new Knight's Landing processor. Okay? And then if you have to move values between the two floating point units, there's a certain delay. So especially that applies to VPU shuffles and that kind of stuff. So there's an additional latency for those instructions basically. There is also, as I was indicating, reciprocals and square root support. So if you can use those instructions, you absolutely should, right? Because then you can get a lot of speed up from using square root vector instructions. And despite the fact that we support masking, again, it enables you to support more patterns in terms of SIMD vectorization, but at the same time, there's a price tag attached to using mask registers. So if you don't have to use them, don't use them. Right? Because some people are kind of tempted to say, well, there's this mask register. I'm a computer scientist. I'm going to set the mask register to all ones. Then it has the same effect as a regular element-wise addition instruction. There's a price to pay for that. Okay, so if you don't need the mask register, don't use it. Okay, retire up here. So this is now the pipeline stage in the whole thing that basically takes whatever has been rearranged by the processor and puts it so that the effects materialize in the memory system the way you wanted them to materialize. So this is now who does the out of order optimizations, and we can retire 2 instructions per cycle. Okay, and then there's hardware threading. All right, so there are, again, 4 hardware threads per core. Now, the thing is, KNL has absolutely been designed so that you can get the maximum performance with just one single hyperthread or hardware thread per core. KNC was different, right? Knight's Corner at times there was a 2-stage decoder, and the way we implemented hardware threading on Knight's Corner meant if you only have one hardware thread, then you would lose 50% of peak performance instantly, just by not using the second hyperthread. KNL doesn't do that, okay? It's closer to hyperthreading on Xeon than it is to hardware threading or SMT on Knight's Corner. Okay, so there are couples of things that are dynamically partitioned. So the reorder buffer, the rename buffers, and the reservation station are dynamically partitioned. And the partitioning automatically adjusts as the threads wake up and go to sleep. Right? So that means if you don't use hardware threading, those resources will not be partitioned. That's what you would expect, right? But there are some resources in the core that are statically partitioned. And if you enable hardware threading, these will cut in half or in portions of 4. Okay? And in comparison to Xeon, we only have a few scheduling points in the pipeline where we can actually switch the hardware thread to another hardware thread. And these are indicated by this red thingy, whatever it is. So, of course, when we fetch from the instruction cache to the decode, we can switch the hardware thread because we might have a penalty when we need to make room memory. Then we can switch to another hardware thread to compensate for that penalty. We can switch anytime we allocate something to one of the pipelines, and we can switch down here when we are waiting for memory. Okay? Or we can switch when we try to retire an instruction. What we can't do is we cannot fill each and every execution bubble in the pipeline as Xeon would do. Right? So there are only a restricted set of scheduling points, and that's important to know. And usually we have pretty good successes with only one hardware thread per core already. Okay, threading. And I'm almost done. You didn't ask questions. Okay, so regards to threading. Ensure that thread affinities are set. Who's good at math? Come on, admit it. Okay, so we have 32 registers, each is 512 bits. How much data is that? Kilobytes, yeah, how many? 2, right. So the register file, and that's just the AVX512 register file, that's not the full thread context, is 2 kilobytes. That means if you swap a thread out, this is 2 kilobytes of data that goes through the caches, and then another 2 kilobytes is pulled in from the memory. Okay? That's a lot of data just to move a thread from one place to another. Okay? So try to avoid that. Okay? Then understand affinity and how it affects your applications. So you've seen the tile architecture with 2 cores sharing the same L2 cache. If 2 threads exchange a lot of data, you should put them as close as possible so that they can work from the same L2 cache and don't have to travel all the way through to all of the cores. Okay? And then, that's now the optimization part. So if you have an individual thread that takes a lot of cache or that has certain things to do, then probably you should have not more than 1 thread per core, or even probably only 1 thread per tile for that particular part of the algorithm, right? And then if you think about the partitioning, a 3-thread configuration kind of seems odd, right? We can cut things into halves if we have 2 threads. We can cut into quarters if we have 4 threads, but we don't cut it into thirds if you only have 3 hardware threads. Okay? At least not the static resources. Okay? And then vectorization, I already kind of said all that. So avoid cache line splits. Gathers and scatters are supported but are bad. If you absolutely have to do SSE, then stick to SSE. Stop mixing SSE and AVX512. Huh? Really? No, I got 15. It's until 11. I'm German, I know that. I'll be on time, trust me. And then use the hardware transcendentals, so the fast math operations that we can vectorize in hardware for as much speed up as you can. Okay, now the untile. Okay, I already said 2D mesh, memory controllers interconnect to the rest of the system. Okay. Again, we don't have an L3 cache. There is no global cache that would optimize data exchange between the individual cores. Right? It's a distributed L2 cache. And a tile can only load in its local L2 cache. This is completely different from what Xeon does, where an L3 cache slice can be loaded from everybody. Okay? Okay, now, it's a mesh of rings. We do YX routing. So first we go in the vertical direction, then we take the turn, and then we go in X direction. It takes about 1 cycle to go in Y direction. So the vertical is 1 cycle per hop. In X direction, it's 2 cycles. It's just latency of traveling on the silicon. Okay. The mesh runs at 1.7 gigahertz. That's kind of fixed. It doesn't turbo up or down. And we support 3 cluster modes, and I will go through all of them. Now the problem is you can only switch those modes if you reboot the system, right? So I think Cray has implemented a solution where you can ask through Slurm or whatever batch management system, and they try to optimize so that when a certain set of nodes is already available in the right mode, they won't reboot them again. But basically what you need to know is that it takes a lot of time to switch those modes, right? And it kind of, I don't know if you account your CPU budget for the reboot or not. That's, accounting issues. Okay, but anyways, you have to reboot the node. That's what I'm trying to say.
What is the limit? Why why is that necessary? What is the limitation? I mean, what is the limitation? I always have this question. So is it something that is kernel related or?
So from quadrant to subnumber clustering, I think it's kernel related. Because here you don't see the NUMA domains, here you see them, and I don't know if the Linux kernel can cope with that. But also from all to quadrant, the location of the tag directories, the distributed tag directory changes. And so you basically would need to flush the whole memory pipeline and the whole chip, which basically means it's a reboot. So probably we can fix it for future platforms. But there's a lot of stuff that needs to be done to change those modes. Okay, all to all. So basically, let's say we are sitting on a certain tile and we have an L2 miss. So we actually need to get the data from, let's say, the MCDRAM up here. Okay, so what we first do is we go in Y direction to locate the row where the tag directory for that data is located. So we travel across the chip to this tile, and we are going to ask this tile, do you know if there is a cache line on the chip? And if not, please tell me what is the memory controller that has that cache line for me. Okay? Then we talk to the memory controller if the cache line is nowhere on the chip. We do the read, and then we transfer back the memory from the memory controller. Okay, so in this case, we travel kind of along the whole chip. Okay, with quadrant, what we do is we modify the hash function that assigns cache lines to tag directories so that the tag directory is guaranteed to be in the same quadrant. That's why it's called quadrant mode, because we have 4 of them, in the same quadrant as the memory controller that has the physical memory associated to that cache line. Okay, and as you can see, the traveling times are a lot shorter in that scenario. Okay, so unless you have a very good reason to do so, don't use all-to-all. First recommendation: use quadrant everywhere as much as possible. Okay, and then there is subnumber clustering, where we do basically the same thing as in quadrant mode. So we have 4 quadrant. There's also subnumber clustering 2, where we cut into 2 hemispheres, bottom and top. But what we do in subnumber clustering is that we expose a quadrant as a separate NUMA node. So you can see them in software. You will see in the NUMA map of the system that there are now 4 sockets, 4 NUMA domains, with local memory and with distant memory. Okay, and then you can program against that. So if you have something like MPI or a NUMA-aware threading implementation in your application, you can use that to gain a little more efficiency because you now know what the quadrants are and where exactly you're running. Okay, OpenMP. Now what's in for the programmers? If you use all-to-all, naturally there is no change, right? It appears as one single NUMA domain. You're all set. That's easy. And SNC4, well, what you see is 4 different NUMA domains. So you need to use first touch optimizations or somehow couple OpenMP and MPI, so that you know that your MPI ranks are scattered across the NUMA domains, and then your OpenMP threads are bound and affinitized within a NUMA domain. Okay? There will be more on that, but just to give you a list of interesting environment variables. So you need to use something like IMPI pin, pin mode, pin processor list, pin domain, and so forth. To control the affinity of the MPI rank plus the core set that is associated with an MPI rank for the OpenMP string. And the other thing is, you don't necessarily need to limit yourself to one single MPI rank per SNC domain. You can have 2 of them, or 4, right? So whatever gives you the best balance of OpenMP versus MPI communication, you should do. Right? The minimum, of course, is something like 1 MPI rank per subNUMA cluster domain, but you can also have 2, and then get better thread scaling within an OpenMP within MPI rank. Okay, and I promised to tell you something about memory latencies. So if you look at this, is kind of a typical picture of how memory latency behaves in comparison to bandwidth drawn from the system. And as you can see, dashed line is MCDRAM, solid line is DDR. It is high bandwidth memory. It is not low latency memory. Okay? So the memory latencies of DRAM and MCDRAM are roughly in the same ballpark. Okay? So if your code is memory latency bound, you will not have a benefit from MCDRAM at all. Okay? Then you can run out of DRAM as well. But the behavior is different. So if you approach the saturation point of DRAM, the curve goes up a lot earlier when you saturate the 90 gigabytes or 120 gigabytes at Broadwell, whereas an MCDRAM you have a longer flat latency that only increases gradually until you hit the saturation point of the bandwidth again. Okay, but the takeaway is memory bandwidth bound you will see a benefit, memory latency bound you will not see a benefit from MCDRAM. All right. And then MCDRAM modes, Hans will talk about that. I will not steal his thunder here. There are different ways to configure the MCDRAM. Again, this is a boot time decision, so you will have to reboot the node to change that. There's a cache mode, so I was talking about there's no L3 cache. We can simulate the concept of an L3 cache by putting MCDRAM into cache mode. There's flat mode where everything is explicitly visible, so you see slow memory and fast memory as NUMA domains, and then there's a hybrid mode where we basically have half of it or a quarter of the MCDRAM as an L3 cache, and the other part is explicitly managed DRAM. And that's it from my side, and I left 5 minutes for questions. Thank you. Turn mine off so that he doesn't hear me breathing. Mine is on.
No. Oh, it is on.
Say something.
Can you hear me? Okay, I'll speak louder. So could you go back to a slide where when we have an L2 miss and how this is resolved? Because I didn't understand.
L2 miss.
The move from step one to step 2.
This one.
So why it goes, for example, that time? Does it send a broadcast message? Who has the others and missing? How does it?
No. So the cache is based on physical addresses, right? And then there's a hash function that tries to randomize the location of the tag directory. So that could mean, if you have 2 consecutive cache lines, the first one goes to that tile, the second one goes to this tile, right? So we try to randomize that. The idea is if we would have, a local tag directory within the same tile, you would see like 32 NUMA domains, right? Where you would have fast cache access and then slower cache access. And what we try to do is we try to randomize it so that it's balances out so that you don't see those NUMA effects. We did the same thing on Knight's Corner also. Right, and with the quadrant mode, we basically, the only thing that we do is we just switch the hash function so that it affinitizes the tile that it computes to ask for the cache line towards where the memory controller is. Right, so it's a little biased for the quadrant where the memory is located.
So in which cases would the auto-wall actually be an advantage?
The what?
In what cases would the auto-wall possibly be an advantage?
Frankly, I don't know. It's kind of debugging. I think debugging, I haven't seen anything where you get all-to-all performance. So the clear recommendation is that it's all-to-all. Heinrich, you... Wait a second until the mic is there.
I read that it's for inhomogeneous memory. If you have not homogeneous memory inside.
Oh, that could be, yes. Okay. Okay. So he said something like if you have a very inhomogeneous memory configuration that you can fall back. But no. I haven't seen a, well, in my enabling life, since I started with Knight's Landing, I haven't seen a case where all-to-all actually makes absolute sense. Right? It's questionable whether you want to use subnumber clustering 4 versus quadrant mode. There, the benefit is rather marginal, I would say. But for all-to-all, I never seen some actual usage. Is there another question? I can try to repeat it if the mic is not working.
I have a question. So you mentioned conversions and diversions of the AVX.
Yep.
And then later on you mentioned that what if someone developed with KNC intrinsics, then maybe you have to redo it with KNL. So if now I've developed something with KNL intrinsics, what would be the outcome for the next generation of the
that is hard to answer. One thing that you will always find is that performance portability gets harder and harder the more you optimize for the machine. And if you do AVX512 intrinsic programming, you kind of start tying yourself to the machine architecture, right? Not so much the instruction set, but more also how the machine executes that instruction set. So there might actually be cases where, even though you have the ideal sequence for Knight's Landing, that another future processor will provide you with less performance than you saw. So that's where, so one thing you could try is recompile it, hoping that the compiler will rearrange your intrinsic code so that it matches better to the new machine, or you will actually have to rewrite it in the sense that you need to, rearrange the code so that it works better, right? But a recompilation will likely be necessary. All right, Hans, your turn to show. Okay, so this is usually a good thing. So raise your hands. I think Maxime will run around with the microphone, and then we should make this as interactive as possible. Okay, agenda-wise, so I have the pleasure to start this. I'm going to tell you about the Knight's Landing architecture, a couple of programming considerations, and the microarchitecture of it. Then Hans pops, so we have this nice acronym codes that we invented for this workshop. Then Hans will take over with how you program this thing called MCDRAM, so the high bandwidth memory that is on this nice chip. Then there are KNL system tips. Whatever is supposed to hide under that agenda item, I don't know. I'm curious to learn that as well. Then we're going to have lunch, and then we're going to talk about the details like compilers, the advisor, all the tools that are somehow associated with Intel architecture and the Intel processors. And you can of course play with that. The next day we're going to focus on MPI, OpenMP, tell you a couple of specifics that are relevant when you want to program for a Knight's Landing, and show you how the latest developments of OpenMP and how you can use that for KNL. And then, there's also an app session where we are going to tell you just a little bit about what we did for applications. It's more like a case study so that you can see what optimizations we did, what effect they had on the code, and so the takeaway should be some recipes that you might find useful for your own code. And then the other thing, day 3, same thing basically. We're going to start with an app session. I'm going to tell you just a little bit about OpenMP 5. So this part is not an Intel presentation at all. And what you will see, and will likely change over the next couple of months, but still, it will give you an outlook on what will be coming in 2018 with OpenMP. And then Hans will tell you a little bit about machine learning, small matrix multiplies, and that kind of stuff that is also relevant for some applications. KNL, Knight's Landing, code name, the now Intel Xeon Phi processor. That's the brand name for it, but I'm going to talk about Knight's Landing and KNL all over the place. Usually the community knows the code names better than they know the marketing nerds. The other thing is, that's probably the most important slide in this presentation, the legal disclaimer, and you can't blame Intel for that, and some other stuff, like trademarks and so forth. Okay, so what I'm going to tell you is, first of all, give you the idea of KNL as a processor architecture. What are the features that you can expect, and that kind of stuff. And then we're going to talk about the core architecture. So that means the individual core, and how they are connected on the processor die. And then we will talk about the untile architecture. So if you know Xeon processors, we talk about core and uncore. And for Knight's Landing, we talk about tile and untile. So everything that is not within a tile is called.
So lunches are for 1 hour and breaks 30 minutes, so please be on time. They will be here in the hall where you got the coffee already. Wi-Fi, it's here, but you also have a folio on your desk. So there is also ETH and EduRAM access if you need for the Wi-Fi. And the video, so everything will be recorded, hopefully properly. And so if you have, so the video will be initially for our internal usage, but we maybe try to get them on the public. That will depend of our interaction with, with procurement and things like that with Intel. And if you have a question, you shouldn't use a microphone. Okay, then otherwise there will not your question will be not recorded on the audio. So with this, I think I'm done, so I'm very pleased. So, Michael, please.
All right, good morning. Welcome. Are you feeling happy? Are you feeling good? Okay, let me change that. All right, so this is the agenda. There's a usual disclaimer I want to make for each of the agendas. It's a rough guideline on what we want to do. If you think that you want to hear on a special topic, let us know and we're going to change the agenda, right? This is your workshop, it's not our workshop. If you want to hear something, let us know and we will tell you about it, all right? And the other thing I would like to make is make this as interactive as possible, okay? The more you ask questions, the less slides I'm going to.
Okay, so good morning, everybody. So my name is Maxime Martinasso. So I'm part of CSCS. So today we have the course on Intel KNL. So first of all, I would like very much to thank all the Intel people here that came and made the course available for us. It's very nice, very appreciated at CSCS. Thank you very much. I also find that it's quite an interesting technology with a lot of capabilities, so I'm very eager to know more about it. So here at CSCS, we have a TDS machine, so a test and development system that contains KNL. So it's a Cray system with 164 nodes. Each node has one KNL, and we will use that machine during the course. So it will be available for us up to 6 p.m. on Friday. So if you need to run things, or if you want to run large jobs and things like that, so we can also run them overnight. So please come to me and we can arrange this. You can also, if you want more, you can also ask for a development project with CSCS if you have access, if you are eligible to run on CSCS machine. That will give you 36,000 node hours that you could use for your development to help you, to develop your application and see the performance on the KNL machine. Regarding the organization of the course, so here's the agenda. You can also find it on the web page where you registered for the course. So we have breaks and lunch, you see.
I think a colleague of mine invented the term. All right, so high-level overview. No Intel presentation without lots of space. It has 8 billion transistors, so it's probably one of the biggest chips on the market. I think only NVIDIA has more transistors to offer. It's manufactured in a 14 nanometer process, so that's kind of bleeding edge technology at Intel and across the industry. It's a pretty fascinating processor architecture. Okay, so, well, it still says coming 2016. I should probably update that slide. But basically, if you have seen Knight's Corner, the Xeon Phi coprocessor, the Knight's Landing processor is kind of a natural evolution of that concept. We forget about the coprocessor thing. We just make it its own bootable processor. It delivers more than 3 teraflops of peak, and I will have a slide in a minute that shows you that we actually do that. There are 16 gigabytes of high bandwidth memory, lots of DRAM, so all the weak points, I would say, of the Knight's Corner coprocessor should have been fixed for the Knight's Landing processor. And it's also not a one-hit wonder. There's also Knight's Hill on the roadmap, and for those of you who have a restricted secret NDA with us and have seen those presentations, you basically already know what will be coming in Knight's Hill. Right, so there's a next generation planned already. Okie dokie. There are 2 major versions.